Hey, welcome back. This is the solutions key to that brief test on isomers and spatial aspects, and I'll go through the answers and solutions and try and anticipate some of your questions. So, question one asked you to show the 7 isomers. I had corrected that. I hope you saw that. I had made that correction in the description of the video, not in the video itself. But I corrected here. There are 7 possible constitutional isomers for the formula C4H6, and here they are. Okay, here are the 7. Not much more to say than that. Obviously, they all share the same molecular formula, and these are constitutional isomers in that interconverting between any two requires making and breaking bonds on different atoms. All right, number 2. Consider the following tri-substituted cyclohexane. A, show the preferred chair conformation. Remember, there are always 2 for this molecule, clearly distinguishing between axial and equatorial bonds. This is the preferred chair conformation where all 3 substituents or attachments are in equatorial positions, and that's only possible because of the 1-3-5 cis tri-substituted pattern for this particular isomer. If you were to flip that preferred chair, you would get a chair where the 3 attachments were all axial, which would be much higher energy. So this is clearly the preferred conformation. And for part B of that question, right, indicate which stereoisomers of the original molecule have at least one bond in an axial position. Here are the 2 possibilities. The one on the left has the 2 methyl groups on the same side of the ring, or cis. They're both trans to the chlorine. The one on the right has the chlorine and one of the methyls on the same side, cis, and the methyls trans to one another. And so in each case, we explore both possible chair conformations. And what we find is that for both of these stereoisomers, there's always at least one chair conformation with at least one axial bond, and the axial bonds are indicated by the purple arrows. All right, and so in this problem, you were told, and this is a surprising result, but the fact is that this particular molecule prefers a eclipse conformation as opposed to a staggered conformation, and that should surprise you. So there's got to be other factors involved that stabilize that eclipse conformation. That's the logic that you follow here. And you're asked to depict this in both the sawhorse representation and as a Newman projection, and then to provide an explanation. So in the upper left is the sawhorse representation of the molecule that you were given in the given conformation, and of course that's a staggered conformation. You can tell because it's a zigzag, fully extended carbon framework. But if you rotate about that bond, as the purple arrow shows, to generate the eclipse conformation, which you can see in the upper right, that's the sawhorse type drawing, and so what you discover, hopefully what you've discovered, is that there's an opportunity for a very stable intramolecular 6-membered hydrogen bond in the eclipse conformation. But it requires the eclipse conformation, so that intramolecular hydrogen bond is that additional force that stabilizes the eclipse conformation. And then looking down carbon 2, carbon 3, you could draw that Newman projection, which you see in the lower right. So you have to look at the chair conformations to understand the overall shape of the molecule, and you're asked about the polarity of the molecule. This is like VSEPR polarity problems that you've done before in general chemistry. So the trans isomer is depicted on the left in its preferred chair conformation, where both chlorines are equatorial, and the cis isomer is depicted on the right, where one of the chlorines must occupy an axial bond. The reason that the trans isomer on the left is a nonpolar molecule with no dipole moment is now seen because the carbon-chlorine bond dipoles cancel each other. Remember, they're vectors, right? And so the one on the left is pointing a little bit up and to the left. The one on the right is pointing a little bit down and to the right, and they add to 0. Whereas the resultant vectors of the cis isomer on the right do not cancel. You can clearly see that when you depict the two chair conformations. So to answer a question like this, you got to draw a lot of cyclohexane chairs, right? Because each stereoisomer, right, has 2 possible chair conformations. You have to analyze 2 for each stereoisomer. So if there are 6 stereoisomers, which there are in this case, that's a total of 12 chair conformations, and you see them here. And so you can see that if you do that, starting at the very top for the 1,2 diisopropyl, okay, the 1,2 diisopropyl, the trans isomer is favored because the trans isomer is depicted in the 3rd chair conformer from the left, right, which is indicated with a purple arrow, and that's where the isopropyl groups are trans and both in equatorial sites. That's why the trans isomer is favored for the 1,2 disubstituted cyclohexane. But in the middle, for the 1,3 diisopropyl cyclohexane, the cis isomer is favored because it's the cis now that can occupy, that the isopropyl groups can occupy equatorial sites. So you're picking the isomer that has an associated chair conformation, right, with as few axial substituents as possible. And then, of course, if we go one more time around the ring and go to the 1,4 diisopropyl cyclohexane, those are the bottom 4 chair conformations. You can see that we go back to the trans, right? The trans, and that's the 3rd structure over. The trans has the di-equatorial isopropyls, and the isopropyls are large groups, so this is a significant effect. Okay, so that should be all of the solutions to this little self-assessment check on your basic understanding of isomers and spatial aspects and conformational analysis. And remember, the idea here is not to master any of these topics or skills. The idea is to get a fundamental basis in them before you actually sit down and do go into detail in your course.